everyone, and welcome to this YouTube channel. So for today's activity, we will be discussing two topics, which are, first topic is the main type of methodologies in the assessment of desirability in economic and environmental or social aspect of constructing a highway proposal. So for the first topic, we will be discussing scheme appraisal for highway projects. So last time we have studied about highway planning. So once a transportation plan has been finalized, a process must be put in place that helps identify the best solution for each individual proposal within the highway network. So each project must therefore be subjected to an appraisal. When we talk about scheme appraisal to a company, it is about monitoring for the employees' performance. While in highway project, it is more different. So the aim of the highway appraisal process is therefore to determine the economic, societal, and environmental feasibility of the project or of group of projects under examination. So the process enables highway planners to decide whether a project is desirable in absolute terms and also provide means of choosing between different competing project options, all of which have the ability to meet the stated goals and objectives of the project sponsors. So the reason choose model of individual or group decision provides a decision making. When it comes to decision making, it undergoes to a different process. So the scheme appraisal process is divided into two broad sections. First is the economic evaluation, and next is the environmental assessment. So, economic appraisal of highway schemes. So, at various points in the development of highway project, the developer will require an economic assessment. So, bakit magkakaroon ng economic assessment? It is because para ma-compare nila yung past performance to the current situation. Para makita nila if they are going to do nothing that will require no work at all, or the do minimum that will be having just an improvement about the traffic performance involving a low-cost upgrading of all the existing facility. Engineering economics provides a number of techniques that result in numerical values term measures of economic worth. So this by definition is considered the number value of money, an important concept in engineering economics that estimates the change in worth of an amount of money over a given period of time. So some common measures of worth are the net present value, the NPV, the benefit or cost ratio, the B or C, the internal rate of return or the IRR. So, bakit nga ba ang center ng ating economic analysis is the money? Kasi nga, meron tayong sinasabi na changes. So, yung value ngayon ng pera is different sa value niya in the future. Economic appraisal techniques can be used to justify a scheme in absolute terms, in which case the decision is made on the basis of whether the project is economically efficient or not. So, kapag lumabas sa ating net present value that a negative net present value or a benefit cost ratio less than the unity would indicate an inefficient scheme where society would end up worse off with the scheme than without it. So the main beneficiaries are those users, and the losers will be the one funding the scheme. So the framework within which the evaluation of the economic consequences of highway scheme takes place is referred to as a cost-benefit analysis. Cost-benefit analysis. It utilizes the net present value technique where the cost and benefits of the scheme are discounted over the time so that they represent present-day values. So using this method, any proposal having a positive net present value is economically sustainable in absolute terms. The main steps in the technique involve the first listing of the main project options, the identification and discounting to their present values of all relevant costs and benefits required to assess them, and the use of economic indicators to enable a decision to be reached regarding the proposal's relative or absolute desirability in the economic terms. So there is a fundamental step in the CBA process. It is the identifying the main project option. So dito, it is where the decision makers compile a list of all relevant feasible options that they wish to be assessed. So when we say the term feasible, it refers to the options that on a preliminary evaluation present themselves as the viable courses of action that can be brought to completion given the constraints imposed on the decision makers such as lack of time, information, and resources. Identifying the main project option. It is usual to include the do-nothing option and the do-minimum option. So the do-nothing option within the analysis in order to gauge those evaluated against the baseline scenario where no work is carried out. The do-minimum option, it offers a more realistic course of action where no new highway is constructed but a set of traffic management improvements are made to the existing route in order to improve the overall traffic performance. Finding the most efficient possible option is the important component on the decision process. So there are many procedures for both identifying and defining project options. So this includes, first is the drawing on the personal experience of the decision maker himself as well as other experts in highway engineering field. Next is making comparison between the current decision problem and the ones previously solved in a successful manner. And lastly is the examining all the relevant literature. Identifying the main project option helps the developer to come up to a best solution or decision that he or she is going to do. So the next one is we need to identify all the relevant costs and benefits. So the primary grouping that contains this type of economic gain is termed user benefits. So the benefits of this type accrue to those who will actively use the proposed installation. The groupings includes the reduction in vehicle operating cost, savings in time, and the reduction in frequency of accidents. Studies might address in some way a secondary grouping of benefits, those occurring the non-users of the proposed facility. So this include, first is the positive or the negative changes in the environment felt by those people situated either near the new route or the existing route from which the new one will divert traffic. So this can be measured in terms of the changes in impact such as air pollution, noise, or visual intrusion or obstruction. And the next one is the loss or improvement of recreational facilities used by the local inhabitants, or the improvement of deterioration in access to those facilities. So the cost associated with the proposal highway installation can fall into a similar categories. Economic life, residual value, and the discount rate. So a highway project is often complex and long-term, with the costs and benefits associated with it occurring over a long time frame, which we term the life of the project. So given that the transport development projects have the potential to be in service for a very long time, it may seem impossible to set a limit on the life of the project with any degree of certainty. So hindi natin masasabi kung hanggang saan ba talaga yung limit ng project. This may not give rise to serious problems in the evaluation. So as the loss of accuracy that results from limiting the life of a project to 35 to 40 years instead of continuing the computation for far beyond this point is marginal to the analyst undertaking the evaluation. The short-term analysis can be justified on the basis that in time equivalent terms, substantial costs and or benefits are unlikely to arise in the later years of the project. So if they are predicted, the life may well have to be extended. technique is applied after a relatively small number of years, the project may well have to be assigned a substantial residual or salvage value reflecting the significant benefits still to be accrued from the project, or conversely costs still liable to be incurred by it. So it is far more advisable to extend evaluation to future point in time where the residual value is extremely small relative to its initial value. So in addition to this, the costs and benefits occur to different times over this time horizon. Because of this, they cannot be directly combined until they are reduced to a common time frame. So this is achieved using another parameter introduced. So it is the discount rate. So discount rate, which translates all costs and benefits to time equivalent values. The actual value used in this social discount rate, given that the decision maker is interested in the benefits and costs of society as a whole rather than to any individual or group of individuals. So it is also a collective discount rate reflecting a project of benefit to a large number of people and spanning a time frame greater than one full generation. The economic life residual value and the discount rate, we will be proceeding to the use of economic indicators to assess basic economic viability. So once the two parameters of the project life and discount rate are set in place, this allows all costs and benefits to be directly compared at the same point in time. So the decision maker must now choose the actual mechanism for the comparing and analyzing the costs and benefits in order to arrive at the final answer for the net benefit of each of the project options under consideration. Value, internal rate of return, and the benefit or cost ratio can be used for this purpose because the net present value, or the NPV, it will estimate the economic worth of the project in terms of the present worth of the total net benefits, while the internal rate, or the return IRR, the IRR will give for each option under the consideration of the rate which the net present value for it equals to 0. And when we talk about the PC, or the ratio based on the ratio of the present value of benefits to present value of the cost. So other supplementary methods of analysis such as cost effectiveness analysis and the payback period could be used to analyze the project options. So it will be discussed by Mr. Loreto.
Now, we'll be discussing about the advantages and disadvantages of cost-benefit analysis. Isa sa mga advantages ng cost-benefit analysis ay yung paggamit ng mga common measurements, money, para mas madaling makapag-compare sa ibang alternative highway proposals. And it also helps a lot when it comes to decision making. Given that the focus of the method is on benefits and cost of the highway in question to the community as a whole, it offers a broader perspective than a narrow financial investment appraisal concentrating only on the effects of the project on the project developers, be that the government or a group of investors funding a toll scheme. The primary basis for constructing a highway project may be societal or environmental rather than an economic one. If the decision is based solely on economic factors, however, an incorrect decision may result from the confusion of the original primary purpose of a proposed project with its secondary consequences, simply because the less important secondary consequences are measurable in money terms. So sa pag-construct po ng highway project, nagkakaroon po siya ng conflict kapag hindi na po nakabase sa primary purpose niya yung mismong project. Knowing na ang primary purpose niya is based on societal and environmental. Kapag sa decision making po, naka-base na po siya bigla sa economic factors, dun po siya nagkakaroon ng conflict. The method is more suitable for comparing highway proposal designed to meet a given transport objective, rather than evaluating the absolute desirability of one project in isolation. Those goods capable of measurement in monetary terms are usually attributed more implicit importance, even though in terms of the overall viability of the project, they may be less significant. Payback analysis. Payback analysis is an extremely simple procedure that is particularly useful in evaluating proposals such as privately funded highways projects, where tolls will be imposed on users of the facility in order to recover construction costs. Example po nito ay mga toll bridge, wherein hindi po siya free for public use. Kailangan pong magbayad siya sa mga toll in order to pass through that para po sa maintenance. Tsaka, the time taken for this equalization occur is called the payback period. It is more usefully applied to projects where the time scale for equalization is relatively short. After po ng payback period, ang mga nakukuhang funds galing dun sa mga tolls ay usually po ay nag-sum up po siya sa initial cost ng project. The method itself does not address the performance of the proposal after the payback period. Its analysis is thus not as complete as the more formal techniques, and therefore its results, when taken in isolation, may be misleading. While the method has certain shortcomings, it is utilized frequently by engineering economists. Its strength lies in its simplicity and basic logic. So, ang payback analysis ay hindi po siya recommended as a primary method kapag nagamitin, kundi pwede po siyang as plan B or pang backup technique, wherein it will be supplementing the information from one of the more comprehensive economic evaluation methods. Environmental appraisal of highway schemes. While the cost-benefit framework for a highway project addresses the twin objectives of transport efficiency and safety, it makes no attempt to value its effects, 62 highway engineering on the environment. So dito po, environmental evaluation therefore requires an alternative analytic structure. The structure developed within the last 30 years is termed Environmental Impact Assessment, or EIA. A central objective of this program was put in place a mechanism for ensuring that the effects of the environment of development projects such as major highway schemes would be taken into account at the earliest possible stages within their planning process. The directive helps ensure that adequate consideration is given to the environmental effects of a development project by providing a mechanism for ensuring that the environmental factors relevant to the project is under examination are properly considered within a formal statement. The directive also details the minimum information that must be contained within the EIS. This includes the physical description of the project, the description of measures envisaged to reduce, remedy the significant adverse environmental effects of the project, and the data required to both identify and assess the main effects on the environment of the project in question. Air quality. Established models are used to predict future levels of these pollutants, and the values obtained are compared with current air quality levels. Cultural heritage. The demolition or disturbance of the archaeological remains, ancient monuments, and listed buildings, and the impacts of such actions on the heritage of the locality are assessed under this heading. Construction disturbance. Nuisances such as dirt, dust, increased level of noise, and vibration created by the process of construction can be significant and may affect the viability of the project. Though this impact is a temporary one, its effect can be nevertheless be severe throughout the entire period of construction of the proposal. Ecology or nature conservation. The highway being proposed may be negatively affected certain wildlife species and their environment or habitat along the route corridor in question. Dito po, habitat may be lost, animals killed, and flora or fauna may be adversely affected by vehicle emission. Landscape effects. The local landscape may be fundamentally altered by the construction of the proposed highway if the alignment is not sufficiently integrated with the character of the local terrain. The land use, the effects of the route corridor on the potential land use proposals in the area, together with the effects of the severance of farmland and the general reduction, if any, in general property values in the vicinity of the proposed route are assessed under this heading. Traffic, noise, and vibration. The number of vehicles using the roads, percentage of heavy vehicles, vehicle speed, the weather condition, where the noise levels are being measured, all the affect the level of noise nuisance for those living near a road. Also, vehicle vibrations can also damage the fabric of buildings, pedestrian, cyclist, and community effects. The severance of community and its effect on the people in terms of increased journey time and the breaking of links between them and the services or facilities used daily by them, such as shops, schools, sporting facilities, and evaluated within the category of impact. Vehicle travelers. This assesses the proposal from the perspective of those using it. Example nito ay yung mga drivers. So ito po ay nakabase sa perspective po ng mga drivers. As water quality and drainage. This measures the effect that runoff from a road development may have on local water quality. Installations such as oil interceptors, sedimentation tanks, and grit traps will, in most instances, minimize this effect, so special measures may be required in particular for water sources of high ecological value. Geology and soils. The process of road construction may be destabilize the soil structure or expose hitherto protected rock formation. Then, policies and plans. This impact assesses the compatibility of the proposal with highway development plans at local, regional, and national level. DMRB advises that an EIT be constructed for all relevant appraisal groups. Three of these are local people and their community, travelers, cultural and national environment. Now we will be moving on to the new approach of appraisal, or what we call NACA. The new approach to appraisal, or NACA, includes a one-page summary of the impacts of each of the projects considered. Within the method, all significant impacts should be measured. Each of these schemes was subject to new form of assessment that incorporated both the COBA-based economic appraisal and the EIT-based environmental assessment. So the AST summarizes the assessment of the scheme in question against the following 5 objectives and their constituent impacts seen by the government as being central to transport facility. First is the environmental impact. Second is safety. Third is economy. Fourth is accessibility. And the last one is integration. Environment. Under environment is noise. The impact of noise is qualified in terms of the number of properties whose noise levels in the year in question for the with proposal option are greater or less than those in the base year. Next is local air quality. The impacts of the proposals on global emissions are assessed using the net change in carbon dioxide levels as an overall indicator. In order to achieve this, the total forecast emissions after the proposal has been implemented are calculated and then deducted from the estimated values for the existing road network. Next is landscape. NATA describes the character of the landscape and evaluates those features within it that are deemed important by the decision made. So dito sa landscape, ang result niya is qualitative assessment, usually varying from large negative to slightly positive, with the intermediate points on the scale being moderately or slightly negative and neutral. So next is biodiversity. The purpose of this criterion is to appraise the ecological impact of the road scheme on habitats, species, or natural features. The appraisal summary tables standard 7-point scale, wherein ang assessment dito is neutral, slight, moderate, or large, beneficial, or adverse is utilized. Next is heritage. This criterion assesses the impacts of the proposal on the historic environment. If 2 is assessed on the AST standard 7-point scale, which is mentioned on the previous slide. Water. In order to gauge the effect of the proposal on the water environment, a risk-based approach is adopted to assess its potentially negative impact on both water quality and land drainage. Both these are evaluated on a 3-point scale of high, medium, and low in an effort to gauge the overall sensitivity of the water environment. Next is safety. This criterion measures the extent to which the proposal improves the safety for travelers, indicating its effectiveness in terms of monetary value, in present value terms, of the reduction in accidents brought about directly by the construction of the new or improved road. Dito po, nagre-require na yung mga aksidente ay ma-broken down into those causing death, those causing serious injury, and those resulting in only slight injury. So yun po yung purpose ng criterion measure na to. Itong criterion pala. Next is economy. The degree to which the proposal contributes both to economic efficiency and to sustainable economic growth in appropriate location is assessed under this heading. So, mga under po ng economy is first, the journey times and vehicle operating cost. The effectiveness of the proposal on this criterion is measured in terms of the monetary value, in present value terms, of the reduction in both journey times and vehicle operating costs brought about directly by the construction of the new or improved road. Next is the cost. The present value of the cost of construction net of the cost of construction of the due minimum option. Next is reliability. This assesses the impact of the proposal on the objective of improving the journey time reliability for road users. Also, reliability is reduced as flows reach capacity and stress level increases. So, stress can be defined as the ratio of the AADP to the congestion reference flow, expressed as percentage. Next is regeneration. This evaluates whether the proposal is consistent with government regeneration objectives. The final assessment is a simple yes or no to this question, based on the extent to which the road is potentially beneficial for designated regeneration areas and on the existence of significant developments within or near the regeneration areas likely to depend on the road's construction. Next is accessibility. This criterion relates to the proposal's impacts on the journeys made within the locality by first, the pedestrians, cyclists, and equestrians. This subcriterion relates to the proposal's impacts on the journeys made within the locality of foot, by bicycle, or by horse. And the assessment should be based on the year of opening, taking typical daily conditions. Next is access to public transport. The extent to which access to public transport by non-motorized modes is affected by the proposal is assessed within this heading. Community severance. The severance effect of those travelers using non-motorized modes is assessed on the standard AST 7-point scale, which is beneficial, adverse, neutral, slight, large. This criterion. Next is integration. This criterion assesses in broad terms the compatibility of the proposal with the land use and transport plans and policies at local, regional, and national level. A 3-point textual scale is used. Ito po ay beneficial, adverse, and neutral. This assessment is intended to be broad brush in approach with marginal changes ignored.
We can say that a highway is functioning effectively if it can assist and accommodate the flow of vehicles with both safety and efficiency. So in order to measure its level of effectiveness, there are certain parameters associated with the highway must be measured and analyzed. These parameters are the quantity of traffic, the type of vehicles within the traffic stream, the distribution of flow over a period of time, the average speed of the traffic stream, the density of the traffic flow. So the process of examining these parameters is termed as traffic analysis. This will directly influence the scale and layout of the proposed highways, together with the type and quantity of materials used in its construction. So let's find out the relationships between the parameters which lie at its basis. The speed, flow, and density of a stream of traffic. To measure the volume of traffic on a highway, we must calculate the traffic flow. Q is equal to N over T, where Q is the traffic flow, N is the number of vehicles, and T is the time interval. So this is the formula on how we will compute the volume of traffic on a highway. The number of vehicles on a given section of highway can also be computed in terms of the density or concentration of traffic. K is equal to N over L, where K is the traffic density, N is a measure of the number of vehicles, and L is the occupying length of roadway. For a given section of road containing vehicles per unit length, the average speed of the vehicles is termed the space mean speed, where U is the space mean speed, L is the length of road used for measuring the speed of the ith vehicle. If the expression for Q is divided by the expression for K, the expression for U is obtained. Q is equal to U times K. Thus, these parameters U, K, and Q are directly related under stable traffic conditions. This constitutes the basic relationship between traffic flow, space mean speed, and density. So let's proceed to speed-density relationship. For example, sa highway may isa nagta-travel ang sasakyan. Ang density nito ay near to zero at ang kanyang speed ay pwedeng tumaas depende sa layout ng road. So yung speed din ay pwedeng tawaging free flow speed sapagkat walang ibang sasakyan doon sa highway. Kapag naman mas marami ang sasakyan sa highway, yung density of the flow will increase and their speed will decrease. At kapag yung traffic ay nagpatuloy, maaaring ang speed ay maging zero sapagkat ang mga sasakyan ay maaaring mag-bumper to bumper or yung tinatawag nating jam density. So, these are the limiting values of the relationship between speed and density. Greenshields propose the simplest representation between the two variables. The speed-density relationship is linear with a negative slope. Therefore, as the density increases, the speed of the roadway decreases. The line crosses the speed axis y at the free flow speed and the line crosses the density axis x at the jam density. Here, the speed approaches free flow speed as the density approaches zero. As the density increases, the speed of the vehicles on the roadway decreases. The speed reaches approximately zero when the density equals the jam density. In mathematical terms, this linear relationship gives rise to this equation. So this relationship between speed and density leads to a set of mathematical relationships between speed and density. The general form of Greenshields speed-density relationship can be expressed as U is equal to C sub 1 plus C sub 2 times K, where C1 and C2 are constants. Combining the equations of traffic flow and speed density relationship, we can derive the direct relationship between flow and density. Therefore, Q is equal to U sub F times the quantity K minus K squared over K sub J, where Q is the traffic flow, U sub F is the free flow, K is the density, and Kj is the jam density. So this equation is differentiated and set equal to 0 in order to establish the density at which maximum flow occurs. So dq over dt is equal to U sub F times the quantity 1 minus 2k over kj is equal to 0. Since U sub F is not equal to 0, then we can arrive at the formula k sub m is equal to kj over 2, where k sub m is the density at maximum flow and kj is the jam density. So its location is shown in this parabolic relationship. So dito naman tayo sa speed-flow relationship. In order to derive the speed-flow relationship, speed-density relationship is rearranged. So by combining this formula with the equation of traffic flow, the relationship is derived as Q is equal to K sub J times the quantity U minus U squared over U sub F. So this relationship is again parabolic in nature. In order to find the speed at maximum flow, this equation is differentiated and put equal to 0. So U sub m is equal to U sub f over 2, where U sub m is the speed at maximum flow and U sub f is the free flow. So combining the equations of density at maximum flow and speed at maximum flow, the expression for maximum flow is derived as Q sub m is equal to U sub f times kj over 4. Paano naman natin madadetermine yung capacity ng highway? So meron tayong dalawang approach. Una ay yung level of service approach. And the second approach that is used in Britain puts forward practical capacities for roads of various sizes and with carrying different types of traffic. So dito sa method na to, economic assessments are used to indicate the lower border of a flow range, the level at which a given road is likely to be preferable to a narrow one. So, mas pagtutuunan natin ng pansin ay yung tinatawag na level of service approach. So, ano nga ba ito? This describes in a qualitative way the operational conditions for traffic from the viewpoint of the road user. It gauges the level of congestion on a highway in terms of variables such as travel time and traffic speed. Meron tayong 6 na level ng service, ranging from Service A, which is the best, to Service F, which is the worst. Service A represents free flow conditions where traffic flow is virtually zero. Only the geometric design features of the highway limit the speed of the car. Comfort and convenience levels for road users are very high as vehicles have almost complete freedom to maneuver. Service B represents reasonable free flow conditions. Comfort and convenience levels for road users are still relatively high as vehicles have only slight reduced freedom to maneuvers. Minor accidents are accommodated with ease, although local deterioration in traffic flow conditions would be more discernible than in Service A. Service C. It delivers stable flow conditions. flows are at a level where small increases will cause a considerable reduction in the performance or service of the highway. There are marked restrictions in the ability to maneuver, and care is required when changing lane. While minor incidents can still be observed, major incidents will result in the formation of queues. The speed chosen by the driver is substantially affected by that of the other vehicles. Driver comfort and convenience have decreased perceptibly at this level. Service D. The highway is operating at high density levels, but stable flow still prevails. Small increases in flow levels will result in significant operational difficulties on the highway. There are severe restrictions on the driver's ability to maneuver, with poor level of comfort and convenience. Service A represents the level at which the capacity of the highway has been reached. Traffic flow conditions are best described as unstable with any traffic incident, causing extensive queuing and even breakdown. Levels of comfort and convenience are very poor, and all speeds are low if relatively uniform. Service F describes a state of breakdown or forced flow with flows exceeding capacity. The operating conditions are highly unstable with constant queuing and traffic moving on a stop-go basis. These conditions and their associated relative speeds and flows are illustrated in this figure. At the level of Service A, speed is near its maximum value, restricted only by the geometry of the road, and flows are low relative to the capacity of the highway given the small number of vehicles present. At the level of Service D, flows are maximized, with speed at approximately 50% of its maximum value. Level of Service F denotes the breakdown condition at which both speeds and flow levels tends towards zero. So, paano naman natin madedetermine yung road's level of service? So, in order to determine a road's level of service, a comprehension of the relationship between hourly volume, peak hour factor, and service flow is vital. So, hourly volume, or B, is the highest hourly volume within a 24-hour period. PHF, or the peak hour factor, is the ratio of the hourly volume to the peak 15-minute flow enlarged to an hourly volume. So PHF is equal to B divided by B sub 15 times 4. The service flow, which is SF, is the peak 15-minute flow enlarged to an hourly value. So ang pagkuha ng SF is equal to B sub 15 times 4. So, after natin ma-determine yung road's level of service, alamin naman natin kung paano na-generate yung maximum service flow rates for multi-lane highways. So, there are ideal conditions proposed by the Highway Capacity Manual. It says that all carriageways are a standard width 3.65 meters. There are no obstructions within 3.65 meters of their edge. There are no heavy goods vehicles, buses, or recreational vehicles on the road. The driver population consists of regular weekday drivers, and the road is divided by a physical barrier and rural-based. So, given the existence of ideal conditions, the maximum service flows can be defined as SF, or the max ideal service flow, is equal to C sub J times B over C times N, where SF max is equal to maximum service flow, N is the number of lanes in each direction, C sub J is equal to the capacity of a standard highway lane for a given design speed J. So its values are shown in this table. tables of values Cj for different design speeds. The maximum ratios of flow to capacity for each level of service and design speed limit are given in this table. So ito yung reference natin mamaya sa solving para malaman natin yung level of service. Let's have an example. A rural divided 4-lane highway has a peak hour volume in one direction of 1,850 vehicles per hour. Ideal conditions apply. Therefore, there are no heavy goods vehicles, buses, or recreational vehicles in traffic. The peak hour factor is 0.8. The design speed limit is 70 miles per hour. Determine the level of service being provided by the highway. The service flow can be calculated knowing the hourly volume during the peak hour and the peak hour factor, which is 1,850 divided by 0.8 is equal to 2,312.5 vehicles per hour. Since the maximum service flow is equal to C sub j times B over C times N, therefore, we obtain 0.58. So under the prevailing ideal conditions with reference to this table, the ratio of flow to the capacity is greater than 0.54 but less than 0.71. The highway thus provides level of service C. So yung nauna ay para sa ideal conditions. Paano naman kapag non-ideal conditions? So ito yung formula para sa non-ideal conditions, where SF is the service flow, N is the number of lanes in each direction, C sub j is the capacity of a standard highway lane, F sub W is equal to the adjustment factor of width, F sub HV is equal to the adjustment factor of heavy vehicles, F sub P is the adjustment factor of driver population, and F sub E is the adjustment factor of highway environment. This table shows the correction factors for non-ideal lane widths and clearances from obstructions. Heavy vehicles such as trucks, buses, and recreational vehicles have a negative effect on the capacity of a highway due to their physical size together with their relatively slow acceleration and braking. The resulting reduction in capacity, termed the F sub HV correction, is estimated on the basis of the amount of road space taken up by each of these vehicle types relative to the taken up by a private car, combined with the percentage of such vehicles in the traffic stream in question. The passenger car equivalent, or PCE, is primarily dependent on the terrain of the highway under examination, with steep gradients magnifying the performance constraints of heavy vehicles. For passenger car equivalents for trucks, buses, and recreational vehicles are defined for three different classes of terrain. Level terrain. This is categorized as gradients or horizontal or vertical alignments that allow heavy vehicles to maintain the same speeds as private cars. Upward and downward gradients of not more than 1 to 2% are normally consistent with this classification. Rolling terrain. So these gradients or horizontal alignments that result in the speed of the heavy vehicle in question being lowered to a value substantially below those of the private car on the same stretch of roadway. The heavy vehicles are not operating at its maximum speed for a substantial distance. The mountainous terrain. Those gradients are horizontal alignments that result in the heavy vehicle operating at its maximum speed for a substantial distance. So, these values are given by this table, the Transportation Research Board table. Having obtained the necessary PC evaluations, the overall collection factor can be estimated once the percentages of the three vehicle types present along the section of road in question has been arrived. PT is for trucks, PB is for buses, and PR is for recreational vehicles. Given these values, the correction factor can be derived. So, ipinapakita ng mga tables na ito yung correction factor para sa driver population and the highway environment. So, ito yung reference natin para sa F sub P at saka sa F sub E. So, let's have an example. A suburban undivided 4-lane highway on rolling terrain has a peak hour volume in one direction of 1,500 vehicles per hour, with a peak hour factor estimated at 0.85. All lanes are 3.05 meters or 10 feet wide. There are no obstructions within 1.83 meters or 6 feet of the curb. The percentages for the various heavy vehicle types are P sub T is 12%, P sub B 6%, and P sub R is 2%. So determine the level of service of this section of highway. The service flow is calculated knowing the hourly volume during the peak hour and the peak hour factor. So SF is equal to 1,764.71 vehicles per hour. So these are the given for F sub W, F sub HB, F sub P, and F sub E. So service flow is equal to 0.92. So this is the formula for the service flow in non-ideal conditions. So using the data from the table of ratios of flow to capacity for different levels of service and design speed, the highway operates at level of service E. So you may refer to the table in the previous slides. So dito naman tayo sa maximum service flow rates kapag 2-lane highways na. So yung kanina ay para sa multi-lane highway, ngayon naman ay para sa 2-lane highways. So ito yung mga ideal conditions para sa 2-lane highways. So under the ideal conditions, the capacity of a 2-lane highway is set at 2,800 passenger car units per hour. If one adjusts this value by a ratio of flow to capacity consistent with the desired level of service, this formula for service flow is obtained. And with that, the service flow is obtained using the ratios of flow to capacity associated with the required level of service as given in this table. However, when conditions are non-ideal, the capacity of the highway reduces from 2,800 PCU per hour based on the following equation. All these correction factors are as defined in the previous sections except for F sub D, which takes account of any unequal distribution of the traffic between the two directions of flow. So this is the table for correction factor for different directional splits on a 2-lane highway. The capacity of the flow in the peak direction decreases as the distribution becomes more unequal. The correction factor for heavy vehicles also depends on the incident level of service. typical values are given in this table. If the level of service values in ideal conditions is not the case, the ratios of volume to capacity for the different levels of service must be adjusted accordingly. Ratios for the different terrain types and for 0, 40% and 100% no passing zones are given in this table. So let's have an example for two-lane highways. A two-lane highway has a lane width of 9 feet with 6 feet clear hard shoulders. There are no passing zones along 40% of its length. The directional split is 70/30 in favor of the peak direction. The percentages for the various heavy vehicle types are P sub T is 10%, P sub B is 4%, and P sub R is 2%. The terrain is rolling. Calculate the service flow of the highway when running at full capacity. Since the road is operating at capacity, the level of service is assumed to be F sub W is 0.76, F sub D is 0.89. Since ang nasa problem ay rolling terrain, the level of service E therefore is for trucks 5.0, for buses 2.9, and for recreational vehicles is 3.3. So yung F sub HB is 0.657. So therefore, given this formula, we can obtain 1,145 V per H. So dito naman tayo sa sizing a road using the highway capacity manual approach. When sizing a new roadway, a desired level of service is chosen by the designer. This value is then used in conjunction with a design traffic volume in order to select an appropriate cross-section for the highway. In order to derive the value for a highway, the annual average daily traffic, or AADT, for the highway is multiplied by a term called the K factor, such that DHB is equal to K times AADT, where AADT is the annual average daily traffic and K is the highest annual hourly value. Typical values for a roadway are K sub 1 and K sub 30, which is equal to 0.15 and 0.12 respectively. Since DHB is a two-directional flow, the flow in the peak direction is estimated by multiplying it by a directional factor D. So ayun, DDHB is equal to K times D times AADT. Yung DDHB naman ay directional design hourly volume. So let's have an example for sizing a road using the highway capacity manual approach. A divided rural multi-lane highway is required to cope with a AADT of 40,000 vehicles per day. A 70 miles per hour design speed is chosen with lanes a standard 3.65 meters wide and there are no obstructions within 1.83 meters of any traveled edge. The traffic is assumed to be composed entirely of private cars and the driver population is ideal. The peak hour factor is 0.9 and the directional factor, which is D, is estimated at 0.6. The highway is required to maintain level of service C. It is to be designed to cope with the 30th highest hourly volume during the year. Calculate the required physical extent of the highway, the number of lanes required in each direction. So DDHB is equal to 2,880 V per H. So we can now calculate the service flow knowing the hourly volume and the peak hour factor as follows. So SF is equal to 3,200 V per H. So in order to calculate the required number of lanes, equation for non-ideal conditions in multi-lane highways can be rearranged as follows. So assuming the following: C sub j is equal to 2000, FW 1.0, F sub HB is 1.0, F sub E is 1.0, and F sub E is 1.0. From the table of ratios of flow to capacity for different levels of service and design speeds, the maximum ratio of flow to capacity for level of service C is 0.71. So the number of lanes required can be estimated as 2.25. So therefore, rounding up, 3 lanes are required in each direction. So I hope may naintindihan kayo about sa basic elements of highway traffic analysis at dun sa mga solvings natin regarding sa multi-lane and 2-lane highways.